In this lesson, we'll be looking at statements and then at truth values. So first, we'll go ahead and define statement. So in the study of logic, a statement is a sentence that is either true or false. And so in this first example, or these first several things, what we want to do is we want to determine if the sentence is in fact a statement. So this says, the Bible is the Word of God. So we want to determine, is this a statement? And if it is it a true statement or a false statement? So in this case, this is a true statement. So we'll put true there. Next one. It says 2 times 3 equals 9. This is a statement. It's either true or false. It just happens to be, in this case, that this is a false statement. So this is false. I'll write it out this time. So I don't want you to, just because it's false doesn't mean it's not a statement. It's a false statement. So statements can be true or false. And the first one was a true statement. Moving on to the next one, x plus 5 equals 23. Well, is this a statement? Is it either true or false? Well, actually, we don't know if it's true or false because it depends on what x is. So this one we would say is not a statement. Life began through the act of creation by God. That is a statement, and it is a true statement. And the last one, I believe 8 plus 7 equals 15. That is a sentence. It's a true sentence, so it is a statement, and it's a true statement. So mathematical sentences can be statements. All right, some things we know. A statement can be negated or made negative. A statement's negation always has the opposite truth value. So if the original statement was true, its negated statement will be false. And then the way that we signify or symbolize negation is this little symbol right here. So we symbolize it with this, and we read this not P. So when we see this, it means not P or the negation of P. So we can negate statements. There's also a couple other things. There's what's called the universal quantifiers. So we use all or every, and you see that symbol there. It's an upside down A. That's the symbol for all or every, and that's how we read this. We would say all something or every. So here we have an example of it. If P, so oftentimes we will use variables or letters to represent an entire statement. So P represents the statement, men are sinners. Then this symbol in front of P means all men are sinners. So all P. Next, there is what's called the existential quantifier. It just means something exists. So you could read it, there exists. We use this backwards capital E for there exists, or one or more, or some, we would say sometimes, but the most specific one is one or more, or there exists. So if Q, again, this variable Q is representing a statement, boys like to play baseball. Then with this backwards EQ, we can say there exists Q, or there exists a boy who likes to play baseball, or some boys like to play baseball. Or, using this phrase up here, one or more boys like to play baseball. And then we can actually negate these statements that have these different quantifiers, but we have to be careful when doing that. And we're going to talk through a couple examples. Remember, the negation of a statement means the opposite truth value. So here we go. We want to negate the next few statements. It says there exists a student who gets straight A's. So if we want to negate this, we have to make it false. So here it just says there exists a student. It means there's at least one. So we can't just say there exists a student who doesn't get straight A's, because that still fits this statement. Just because there exists a student doesn't mean it's all students. So in order to negate this, we have to say no one gets straight A's. So we would write no student gets straight A's is the negation of P or not P. Next, we want to negate some pies are not cherry pies. some are not cherry. Well, we can't just write some pies are cherry pies. We can't just take out the not, because if some pies are cherry, that still means some pies are not cherry. So we have to say all pies are cherry pies, would be the negation of Q. So this one was interesting because Q was already a negative statement. So not Q has to be kind of a positive statement. It doesn't have the word no or not in it. Next one, no square is a circle. So statement R represents no square is a circle, which means none of them. No square is ever a circle. So what could we do there? We just have to negate that. We don't need all squares to be circles. We just need to, for there to exist a square that is a circle. So the negation of R would be there exists a square that is a circle. Now remember, what we're writing here, just because we're writing not R, it doesn't mean the statement's true. So they should have opposite truth values. So this statement is true. No square is a circle, which means this one is false. Now we're going to look at this idea of what's called truth tables. And a truth table tells all the different possibilities of things that could be true or false. So here's the truth table for negation. So let's see if we can talk through this. So this is saying the statement P, again, definition of statement, it's either true or false. So in this case, we're saying we have some statement P, and here we say P is true. Well, if P is true, what does not P have to be? Well, it has to be false. Well, what about P? Could it be anything else but true? Well, yeah, P could be false. So if P is false, not P would have to be true, because these have to have opposite truth values. We'll get more into truth tables as we work through different things here. Just like in sets, we have a couple operations that we can think of with statements. So first we have a conjunction, and a conjunction is a compound statement, so putting two statements together by connecting two statements with the word and. So the conjunction P and Q is denoted like this. We use this little symbol. Kind of reminds us of the symbol we used with sets for and. For sets, we used this. So this would be an and for sets. Well, we have the upside down V for and for Q. And this would be statement P and statement Q. The next one is a disjunction, and that's a compound statement formed by connecting two statements with the word or. And here you see the symbol for or. When we're talking about statements, remember for sets, we used the symbol that looked like that. So a V for sets, a U looking one for, we called it union of sets. Sorry, and the V for statements. So that's a disjunction. So here's a truth table for conjunction. And what we see here is we're now working with P and Q, so we actually have two statements. And when we have two statements, two different statements, we're actually going to have 4 rows here. And so let's talk through that. What we're going to always do is 2 to the number of statements here is how many rows we're going to have. And when I say number of statements, those are the different letters that appear. So we have a P and a Q, that's only 2. So 2 to the number of statements. So in this case, we have 2 squared, which is 4. And the reason this number is 2 is because we have 2 options. We have true or false. That's what this 2 has to do with. So the base always stays 2, and the number of statements could change. So if we had 4 statements, we would have to do 2 to the 4th. Like maybe we would have P, Q, R, and S. We would actually have to have 16 different rows here with trues and falses. So that's how you can tell how many rows you're going to have. Really, another thing you can do is you can list all possibilities. And so if we have 2 statements, we could have both of them being true. We could have the first one true and the second one false. We could have the first statement false and the second statement true. Or both statements could be false. And so let's think through this. If both statements are true, then P and Q is true. So and means both have to be true. If both aren't true, P and Q is not true. So this is actually another kind of statement in itself, P and Q. So we're stating, is this true? Well, it's true only if both P and Q are true. P is true, Q is false, so therefore P and Q is false. P is false, Q is true, so therefore P and Q is false. And obviously, if both statements are false, the conjunction is false. Then here's the truth table for disjunction, or. And so remember, this means or. And so when you make an or statement, all we need is one of those statements to be true, at least one. So here they're both true, so our or statement is true. Here P is true and Q is false. Well, at least one of them is true, so our or statement is true, P or Q. Again, one of them is true. In this case, it's the second one, so that's true. But here P or Q, both of them are false, so that statement would then be false. All right, true or false. Any 3 points are collinear, or the union of opposite rays forms a right angle. All right, so this is an or. So it's a disjunction. So we need just one of these statements to be true. So is the first one true? Any 3 points are collinear. Well, that's not true because I could choose 3 points that are not collinear. So we could have 1, 2, 3. Those are not collinear, so that one's not true. Let's look at the next one. The union of opposite rays forms a right angle. Well, if we take opposite rays, so opposite rays lie along the same line and they have a common endpoint, does this form a right angle? It does not. So in fact, this is a false statement. We have, like, here's our P, here's Q, we'll make it wavy. That's Q. Well, neither of those are true. So P or Q is false. All right, here's the next one. Make a truth table for P and then in parentheses, Q or not R. Well, let's work our way through this. This might take a little time here, but it's good to think through these. So how many different statements do we have here? We have P, Q, and not R. So we have 3 different statements, P, Q, R. And so how many rows do we need to have? Well, it's always 2 to the number of statements, and we have 3 statements. So we should have 8 rows of trues and falses. And so we'll need 8 rows. All right, so there's our 8 rows. Now what we do is we list each of our statements just individually. So we have P, Q, and R. And what we want to do here is we want to list all combinations of true and false. So here we go. They all could be true. So we try to do this orderly. Now, the first 2 could be true, and the last one could be false. The first one could be true, the second one false, and the third one true. And the first one could be true, and the last 2 could be false. So those are all of our combinations where P is true, and then our other different things with Q and R. Well, now we can kind of do the same thing when P is false. So P could be false, and the other 2 could be true. P is false, and the first Q is true, but R is false. P is false, Q is false, but R is true, and then all of them could be false. So there are the 8 different possibilities we have for P, Q, and R. So now what we're going to do is we're going to work our way through here. There's an order of operations here, similar to what we do with arithmetic. So we have parentheses, so we want to do what's inside here first, but even within the parentheses we have this not R. So let's go ahead and write the truth values of not R. Now obviously not R can be true or false, but we have to look compared to all of our rows, and not R will be the opposite of R. So all we have to do to find not R is do the opposite of R. So here it's true, so false. Here it was false, so we're not R is true. True, so we're going the opposite. False, false, so true. So it looks like this one's just going to alternate the whole way down. This one's false, so we do the opposite. True, and then false, and then true. So there's not R. Well, what do we want to do with not R? Not R is combined with Q, and this is an OR. So we want to look at our not R column and our Q column and combine it with OR. Now remember, OR just means we want one true between the two things. So we're going to go ahead and write Q or not R. We're making a brand new column, and we're going to have to look at these two columns, Q and not R. And remember what I said, this is an OR, so all we need out of the two of those is a true. So here's a true and a false. Well, that's okay. We can have a true because one of them was true. True and true. False and false. Well, false and false gives us a false. We need both, at least one true. False and true. Well, at least one true, so there we go. True and false, so at least one true, so it's true. True and true. False and false. Well, that's a false. And then false and true. There was at least one true, so true. And now what we want to do is we want to take what we just got here, which was in this column, and we want to combine it with P with an AND. So AND means both those columns. So we're going to look at this column compared to this column, and we need both of them to be true. So now what we do, we're going to put another column header, and we're actually going to do the whole thing now. This is our last step, P and Q or not R. So I put too much space here, but that's okay. And again, we're looking for true in both of these columns. So we have a true and a true, so that is true. True and true, so that is true. True and false. Well, we need both trues, so that's going to be false because it's an and. We need both trues. True and true. False and true, so it's false. In fact, the rest of our P's are false, so no matter what's here, it's going to be false because we need them both to be true, and we can just look at that first column and know that they're not both true. And so here is a truth table for P and Q or not R. And that's how you do that truth table.